This is number 73 in chapter 16. It is a titration question, and it's a very involved titration question. We have multiple parts, A through F, but we are basically beginning with a 25 milliliter sample that is 0.17 molar in methylamine, and we are titrating that with 0.150 molar HBr. So we are titrating a weak base with a strong acid. One thing we're going to have to look up is our Kb for our weak base, and we can get that from our table. So that's our Kb, and so we have a number of questions here. The first question is asking us about the initial pH. And so if we're asked, an initial pH for a titration question, we have to know, right? This is really a chapter 15 question. It's really just asking, like, if you have this much base, well, what is the actual pH? So for a lot of these things, we need to really keep in mind always our equilibrium reaction. So let's write this at the top. And so that is our reaction, our equilibrium reaction. We have our methylamine base acting as a base and generating its conjugate acid, methylammonium, and then also hydroxide. So for our initial pH, we're really just looking at a Kb expression with our products over our reactants. We covered a lot about ice tables in chapter 15, so I'm not going to go through an ice table demonstration again for this, but the realization, right, for these types of problems with an ice table is that our Kb is going to be equal to essentially x squared over our initial concentration minus x. And again, we are going to assume that it's going to 0 due to the small value of our Kb, because this is a weak base. So we bring over our 0.175, we would end up with x squared being equal to 7.7 times 10 to the negative fifth. And if we take the square root, our x, remember, which is equal to our hydroxide concentration, because that's what we are producing, that is equal to 8.774 times 10 to the negative third molar. So that is our hydroxide concentration as a result of starting with that concentration of weak base. Our POH would equal the negative log of that 8.74 times 10 to the negative third. Our POH is then equal to 2.05. If we then do the conversion to pH, right, 14 minus 2.05, we get our pH initial. We should expect a basic pH, and we do receive that with 11.95, again because we are generating hydroxide according to that equilibrium. So that's part A, just what is the initial pH, and again, that's a basic chapter 15 question that we covered also with exam 2. Part B asks us about the volume of added acid required to reach the equivalence point. So we're asked, what is the volume of this HCl to get at the equivalence point? And remember, that's where moles of our base is going to equal moles of our acid. So we have moles of base and we're titrating that with moles of acid, but at that equivalence point, that's when those two mole values are actually equal. And so basically what we're talking about is our neutralization process, our methylamine that is going to be reacting with HBr in a forward process, right? This is not an equilibrium. To generate our conjugate acid and Br minus, right? We don't have to worry about Br minus because it's a spectator. It doesn't affect pH. But this is what's happening. We're destroying or neutralizing all of this base with our addition of strong acid to generate its conjugate. So this is basically this type of setup, right? If we have a molarity and a volume of our base, well, that's going to equal the molarity and volume of my acid, right? Because we want the moles of base to equal moles of acid. And that's what we get when we multiply molarity by volume. So that means we can take our concentration of our base times its volume, and so that's going to equal the concentration of the acid that I'm using times that unknown volume, right, for the equivalence point. And so the volume is 0.0291 liters. So that is our volume of added acid in order to neutralize all of the starting base. So that's part B, but I'm going to kind of keep that value up here. The volume for that equivalence point is 0.0291 liters. That's part B. Part C is looking at a point in between the equivalence point and the initial pH, or the initial point. What is the pH at 5 milliliters of added acid? So what is the pH after we add 5 mils? So now this is really a question of moles to moles, right? Because again, we have to remember that this is the process that's occurring. As I add HBr, I'm making the conjugate acid of my starting base. And so since this is a one-way reaction, that means it's just a mole-to-mole ratio. So if we know how many moles of HBr we've added, well, then we know how many moles of our conjugate acid we formed. We also know how many moles of our starting parent base is actually left over as a result of that addition of HBr. So that's the first step, is to look at your concentration and get this into a mole value, 4.3, or I'm sorry, I'm looking at the wrong spot, 7.5 times 10 to the negative fourth. We also need to figure out how many moles of our parent base we have. So we take our concentration times the volume of the sample to give us moles of our starting parent base. And so we are going to now subtract. We have this many moles of our parent base, and for every mole of acid, right, that's going to take away a mole of that base. And so we end up with 3.625 times 10 to the negative third moles of our methylamine left over. And again, if we begin with 0 moles of our conjugate acid, for every mole of that strong acid that is added, we form a mole of that conjugate. So that is our two new mole values, our 3.6 and our 7.5 times 10 to the negative fourth. And so we're going to use those mole values to now get new concentrations. We have our 3.625 times 10 to the negative third moles of that methylamine. And here's a trick, right? We added 5 milliliters to our original sample of 25 milliliters, so now we're in really 30 milliliters or 0.03 liters. And so that gives us our concentration of our methylamine. And then we're going to do the same thing for our conjugate acid. And so now, technically, we have a buffer, right? We have concentrations of our starting parent base. We have concentration of its conjugate acid. And so we can now use the Henderson-Hasselbalch. And so we would have our POH being equal to our PKB plus the log of the concentration of our conjugate over our parent. So we need to use these two values in our ratio, and then we also need to take the negative log of our KB. So let's begin there. We have our POH is going to equal that negative log of our KB, the 4.4 times 10 to the negative fourth, plus then the log of our concentration, 0.025 over 0.1208. And so that means our POH is equal to 3.356 plus the log of that ratio, which is 0.206. Our POH then is equal to 3.356 plus a negative 0.682. 2.4. And now we know our pH. Or I'm sorry, our pOH. Our pOH is then equal to 2.671. And then if we subtract that from 14, we get a pH of 11.329. So there is our pH. We should expect it to be basic because we have not reached the equivalence point, right? And so that means we still have excess parent base. And so we see that with our basic pH. So that's part C. Part D is looking at another part of a titration that's in between the equivalence point and the initial point, but it's a special part, right? It's actually halfway between that initial and equivalence point. And so that's a special scenario, because if we look at our neutralization process or our titration process, halfway between would mean that we would have the same amount of moles of our parent base as we have of our conjugate acid. So if we have the same moles and we have the same volume, then that means our Henderson-Hasselbalch simplifies to an easier expression. And so again, halfway between the equivalence point would mean that our moles of our methylamine would equal our moles of our NH3, right? Because if it were at the equivalence point, then all of this would be converted into our conjugate acid, but halfway, that means we have equal mole values, and because we're in the same vessel here, our molarities then are also the same. If we look at our Henderson-Hasselbalch, that means our pOH, which equals our pKb plus the log of our concentrations of conjugate over parent. This is really saying the pOH is equal to the pKb plus the log of 1, right? Because this concentration is equal to that concentration. The log of 1 is 0, and so what that is saying is that at this special point, our pOH is actually going to be equal to our pKb. And then from that pOH, we can get our pH. So that's all we need to do for this type of question, is realize that halfway in between those two data points, those concentrations are going to be equal. And so we can prove that, we can actually look at what the molarities are and actually go through the process again. If we do that process, I'm just going to kind of skip a little bit. In part C, we had 4.375 times 10 to the negative third moles of that methylamine base, and then in halfway we should get a value of 2.182 times 10 to the negative third moles of our HBr that's going to be added. The difference of that is 2.193 times 10 to the negative third moles. And then if we divide that by our volume of 0.0395 liters. Again, we have to realize this would be a volume that is halfway between the equivalence point and the initial. Our equivalence point is 0.0291 liters. So we're adding roughly, 14.5 milliliters to our starting solution of 25 milliliters. And so when we take that, we get a value of 0.0555 molar in our CH3NH2. We can do the same thing. So we still have that 0.0555 molar of that base. We can do the same thing with the conjugate, right? We began with 0 moles of that conjugate, and we're basically adding 2.182 times 10 to the negative third moles of that HBr. And so now that gives us a value of 2.182 times 10 to the negative third moles of that conjugate that is formed. And so that would be then divided by our volume, again the same 0.0395 liters, to give us a value of, it's close, it's a little bit different, 0.0552 molar in that conjugate acid concentration. So we have 0.0552 and we have 0.0555. I mean, these really are the same concentrations. And if we go further and plug it into our Henderson-Hasselbalch, right, our POH was equal to our PKB, right? And remember that PKB was equal to 3.356. And so we're going to take the log now of those two new concentrations. Our conjugate was the 0.0552, and then our parent was 0.0555. And so that means our POH is equal to 3.356 plus a negative 2.353 times 10 to the negative third. Very, very, very small value. Our POH is then equal to 3.353, and that means our pH is then equal to 10.647. So as we go through the titration, now halfway in between the equivalence point, we see a slow drop that's occurring in the pH. But again, this is a special point halfway between the initial and the equivalence, is when you can say that our POH is equal to our PKB for this example. Our POH was equal to 3.353. Our PKB was equal to 3.356. A little difference, but pretty much exactly the same. If we were to do a different type of question and we're looking at maybe a weak acid in the titration, we would have the same effect, but now you would have something that would look like that. Our pH would be equal to our pKa. But since we're talking about the titration of base, that's why it's this relationship. So that's part D. Again, a special point halfway between the initial and the equivalence point. Part E is looking at the pH at the equivalence point. And so what we have to realize is now that the equivalence point, since our moles of our base equal the moles of our acid, we have converted all of our methylamine starting base into the conjugate acid form. That means that this is not a starting material anymore. For this part, now we have to realize that once we're at the equivalence point, we are now beginning with the conjugate acid. And so as a result of that, we simply have a Ka expression, which is going to be equal to our products over our reactants. This is really a chapter 15 question, but starting with a conjugate acid. So it's a conjugate question. So that means we need to solve for our Ka, which is going to be our Kw over our Kb. And so that Ka is going to be 1 times 10 to the negative 14th over our Kb to give us a new value of 2.272 times 10 to the negative 11th for our Ka for this equilibrium. Again, we kind of have the same thing with our ice table. I'm not going to go through the ice table, but if we use it, we should be able to come to this equation. Our Ka is going to be equal to essentially x squared over our initial concentration of our methyl ammonium. So we need to detail that concentration. That concentration is going to be equal to the amount of moles, and remember we started with this many moles of our methylamine, but now that we're at the equivalence point, all of this has been converted into the conjugate. So that's how many moles of the conjugate we have. The equivalence point was 0.0291 liters. When we add that to our 0.025 liters of sample, we get 80.8 milliliters, or 0.0808 liters, to give us our new concentration of, oh, I'm sorry, let's go back. We add those two volumes, we get 0.0541 liters to give us our concentration of 0.0808 molar in that now starting conjugate acid. And so that's what's going to go there. So again, this just comes from the moles that we started with of our base. At equivalence point, now that's how many moles of our conjugate we have. That's really what we're beginning with here. We're just dividing by the new volume, which is our 0.0291 liters, plus our 0.025 liters of our sample. We solve for that. Our x squared is going to be equal to 2.812 times 10 to the negative 10th. Our x, which again, remember in this case is our H3O plus concentration is going to be equal to 1.677 times 10 to the negative fifth. And so our pH should be equal to 4.775. So again, at the equivalence point, since now all of our starting parent base has been converted into the conjugate acid, that is the expression we need to use. And so as a result of beginning now with our conjugate acid, we are generating H3O plus, and we should be in an acidic area, which we are, pH less than 7. So that is part E. The last part F, is looking at past the equivalence point. So pH when you're 5 milliliters past the equivalence point. So we have to do some similar things here. Let's figure out our new mole value, because now what we have to do is figure out, well, since we're past the equivalence point, how many moles are we past the equivalence point? And so if we're 5 milliliters past the equivalence point, we take our 0.0291 and add our 0.005. We get our new volume of 0.0341 liters to give us our mole value of HBr that's been added. Again, this is in excess. And so we want to subtract that from what we began with. And we began, again, this goes back to the earlier part of the question. We had 4.35 times 10 to the negative third moles of that starting methylamine. So that is our moles of our methylamine. This is now how many moles of HBr we've added. And the difference of that is 7.4 times 10 to the negative fourth moles of excess HBr. Right, remember HBr is a strong acid, so that's really saying H3O plus. So we can really say that's moles of excess H3O. And if we divide that by our new volume, right, because we added our 0.0341 liters to our 0.025 liters, we get a concentration of 0.0125 molar. And again, that is our excess HBr. Again, after we take the difference between that and our methylamine. So we have 0.0125 molar excess of our H3O plus, and so our pH is simply going to be equal to the log of that value. And we get a pH equal to 1.902. And so when you're past the equivalence point, again, you're just trying to determine what is the excess that I have. In this case, we have excess acid, but again, that could also be excess base, depending on the question. That is number 73.